So let's look at another hypothetical situation where I just want to illustrate here the fact that p-hacking isn't necessarily always just a case of having lots of variables that you're looking at and that you need to correct for. It can take rather more subtle forms. And a lot of it is to do with post hoc, looking at your data and then sort of changing how you analyze it depending on what you see. So here's an example where maybe we're looking at a drug effect and we've got people of different ages. And again, 0 would mean there's no improvement in your symptoms. And what you see here is that overall, there's really no effect of this drug at all. It's not improving anxiety. But then we notice that there does seem to be some sort of effect going on. If you look at people over the age of 36, you can see that all of them seem to have improved to some degree. And this is a sort of thing that people do rather a lot. And it's sort of, again, it's got a p-hacking flavor to it because it's looking at the data and then thinking about how to analyze it. Question is it okay to run a statistical test then and just report an interaction? For example, dividing people into old and young and saying, well, there is an effect, but it only affects the older people. The answer is that you really shouldn't be doing that because it's misunderstanding statistics and it's not taking into account, again, the context in which you've observed that result. It is okay to say that you observe this association in exploratory analysis. It suggests a new hypothesis, but would need to be tested in a new sample. It's not okay to pretend that you predicted it in advance and to find all sorts of literature that might sort of support this. And what's really not okay is to forget about the people aged under 36 and only report the data that supported your hypothesis. But again, this is something that unfortunately people tend to do. And this is really getting at the nub of the issue, which is, and I will keep saying this because it gets missed, you can't use the same data to develop a hypothesis or to generate a hypothesis and to test the hypothesis. If you start doing that, then the interpretation of p-values is completely invalidated because the p-value is on the assumption that you haven't seen the data before you've formulated your hypothesis, and the results make sense if you adopt that approach, but not otherwise. But again, that's all rather theoretical. It can be quite interesting to use simulations to show it. But before I do that, I'll just show you another type of thing that happens a lot, which is the Garden of Forking Paths. That's the title of a short story by Bourget, all to do with how life's choices, you can make what seem like rather arbitrary choices and your entire life is influenced by them. In analysis, you can see similar things. So this is just a fictitious example of having a large population database that's used to explore the link between attention deficit hyperactivity disorder and handedness, for example. Suppose we've got a big sample and we don't find any difference between groups in handedness relative to ADHD. But then we notice that in the younger kids, there's sort of some suggestion of an effect. And we think, well, there's something possibly going on there, but we've now divided our sample into two. And then we go on and say, well, if we had actually two different measures of handedness, a skill measure and a preference measure. And on the skill measure, it's looking more promising. So we divide it yet again. But what's happening here is every time we make a subdivision, we should be correcting for the number of terminal points here. These 4, at the moment we've got 4 possible routes we could have taken through. And if we're only following this route because the data pointing us in that direction, that's disobeying this rule about testing, formulating and testing a hypothesis in the same data. And the probability here is that, the problem here is that the probability of a significant p-value less than 0.05 at any one of those points is now as high as 0.19. Again, what you're really thinking of is the opposite of the probability that nothing is significant. And that gives you that value of 0.19. And we can go on, we can subdivide into males and females, and you see this probability of something coming out as significant going up and up and up. And by the time we've got to then dividing them into urban and rural, we've actually got a better than 50% chance that one of these is going to be significant. But if we're only focusing on the one that's looking most promising, so we've got young urban females on the measure of hand skill, we might be getting very excited at p less than 0.05, but actually it's really only meaningful if you can still get something coming out when you've corrected for all these different possible comparisons you might have done. There's a beautiful real life example of this. This is, I'm afraid I haven't got a link for this, but it's, I think, paywalled now on the Washington Post. But if you just Google dazzled by tortured data, there's a story about Richard Peto, a statistician here in Oxford, doing big trials of drugs for heart attack, who got a null result on a huge trial and sent it into the journal. And then the journal editors and the reviewers started saying, well, what about looking at subdivisions? I mean, what about just looking at patients who had this particular characteristic, or males or females or whatever? And Peto was aware of the Garden of Walking Paths and said, no, we're not going to do that. That's not valid. But they pushed, and in the end, he really got his own back by saying, okay, if you really want me to subdivide them, I'm going to subdivide them by astrological sign. And of course, there's 12 astrological signs, I think. And he found that there was one astrological sign where the drug appeared to work. And he's making a point that you can always find something if you start subdividing your data. But that was a really classic illustration, and it's published in the journal, the analysis by astrological sign. There's another example as well that is in this story about people who've got the letters G, Y, or N in their last name. I think they're 5 times more likely to have gynecological problems or something. But it's this post hoc subdivision that is the problem. This concern has been around for years. De Ruyt, who's a very famous Dutch psychologist in the 1950s, wrote this beautiful paper that nobody took much notice of because it was in Dutch, but it was translated in 2014. And it really makes these points about needing to distinguish between whether you're hypothesis testing or hypothesis generating in the research you do. And exploratory research where you don't have a hypothesis is fine, but you can't interpret p-values in that case. You use those sorts of analyses to generate your ideas, but then test them in another sample. And again, you cannot use the same data to generate a hypothesis and test the same hypothesis. So p-hacking, which takes many forms, but is always this sort of subdivision of data according to where you start doing the analysis on the basis of what you've observed, is leading to a high rate of false positives and a distorted literature. This is a rather nice mnemonic for understanding the difference between type 1 and type 2 errors. The type 1 error is that false positive error where you think you've got something, but really the data are compatible with a null result. And we will be talking about type 2 errors when we come on in part 2 of the course to look at statistical power, where you've actually got a result, but you don't pick it up. I love this mnemonic that somebody gave me to remember the difference between type 1 and type 2, which is the boy who cried wolf. Those of you who know that story know that it's a boy who cried wolf, and he did it so often people stopped believing him. But then when a wolf really came along, everybody got eaten because they didn't believe him anymore. So he was initially making a type 1 error, claiming there was a wolf when there wasn't one. The final prediction was that there really was a wolf, but nobody believed him. Here's an optional exercise. It's a bit tedious to do this, but I've put it up for those of you who are keen to try with your little Excel spreadsheet. It's an exercise that starts to indicate the limitations of doing things in Excel, because really you'd need quite large numbers to do this properly if you wanted to simulate the sort of forking paths situation that I had shown you before. But you can do that, and what you need then is you don't need lots of variables, but you need lots of things like these categorical things that you're going to subdivide your group on. So you've already got a variable called group where people are 1 or 2, but you could add sex, you could add age band and things like that. And the reason I put this up here is if you want to do that, and I'll go into Excel just to show you this formula, if you want to create binary variables, it's not that difficult to do. If I wanted to create, for example, a variable called sex, I could do if, so this is our random number between 0 and 1. If it's a greater than 0.5, we'll allocate you to 1, and otherwise we'll allocate you to 0. And if we just pull that down, they're all 0 at the moment because we have to do calculate now. But then you see it's 50% roughly 1 or 0. So you've got a completely arbitrary designation, and you can do that for other variables. And then you can start to see, are there particular variables that seem to bring out significant differences between groups? And it's a similar picture as to when you've just got lots of variables, but you start to understand how easy it is to generate false positives if you have enough variables in there that you're going to look at. And certainly astrological sign, where you've got all these different versions, is a goldmine for finding things like that. But let me just go back to my slides here, because I've just got one more to put up for discussion points. And here I'm suggesting that this is something we could discuss, but when you read a published paper, how can you tell if the results have been p-hacked? And then there's some thought experiments. Suppose you test a reading intervention, you've got 4 outcome measures, and only one of them is significant at 0.05. Is it acceptable to drop the other outcome measures from your report? Or suppose you test an intervention with just 1 outcome measure and results are significant for boys but not for girls. How should you write up the findings? These are issues that get to the nub of the difficulties that arise if you start subdividing your data post hoc without having had an initial hypothesis. But I'll stop there and give you a chance to think about that before we come on to the next bit of the course. And then we'll start looking at how to do some of the things you've been doing in Excel in R.